In this video, Dr. Jonti Horner is going to present a summary of the topic, How Do Stars Shine?
Right folks, so that's it for the course videos for Everyday Physics. That's the end of the final topic. In this final topic, what we've done is taken a number of different ideas that you've come across throughout this course and shown you how you can apply those things which at the time probably seemed very specific to the topics you were studying, and shown you how you can apply those to very different fields. And it's one of the key points about physics, which is often overlooked even when you're being taught it, that the facts and the techniques and the theories you learn from one part of physics are applicable throughout a wide range of other aspects, not only of physics, but astronomy, biology, engineering, chemistry. It's very, very useful to try and spot these links between subjects. And so to highlight that, what I've brought to you today was using those tools to learn how stars are born, how they live, how we can learn more about them using the tools you've learned in this course. And hopefully that's been very helpful. Hopefully you've also been able to spot some links between the information you've learned here and the everyday physics that you use both in your day-to-day life at home and also the other courses that you're studying. Hopefully we've been able to give you some idea of the web that links all of these things together. The end of the day, we're a narrative species. We explain the way the world works by telling stories. And the stories we tell may appear to be focused on a very narrow area, but they're often applicable well beyond the boundaries that you set when you learn them. And it's very important to keep in mind that the theories that we tell you are not necessarily hard and fast absolute rules, but they're the best stories that we can come up with to explain the way that the universe works, to explain the world that we observe. We are, after all, the storytelling ape. So what we've done today, then, is taken the stories you've learned earlier in this course and applied them in a different way and shown how we can use those ideas to learn more about the world around us. In particular, then, we've learned about how stars are born, the processes through which the stars shine, why the stars are different colours. We've learned about why some stars are much more luminous than others, and why some stars live far longer and some stars live for a shorter period of time. We've even learned how we can work out what the stars are made of. Now, the stars that we see in the night sky are huge distances away from us. The very closest star to us is a star called Proxima Centauri. It's a tiny little red dwarf, much, much less massive than the Sun. The light from Proxima Centauri takes just 4.26 years to reach us, travelling at 300,000 kilometres per second. It's so faint you can only see it with binoculars, even though it's our nearest stellar neighbour. Most of the stars you see in the night sky are hundreds or even a few thousand light years away. The light's been travelling from them for a huge period of time, and so we can't just travel to these stars and sample their atmospheres, but by using the spectroscopic tools that we've talked about, we can learn what stars are made of. And an important point about astronomy is that astronomy is really the only science that is a purely observational science. Almost everything we look at is too far away from us to go there and carry out experiments on it. You can't put a star in a test tube and play around with it. So everything we've learned about astronomy, we've learned purely by observation. And so these tools, like looking at the spectra of stars, are incredibly important to us as astronomers. And the final thing I've shown you in this is how we can take those tools one step further and use them to work out how planets move around stars, and we can use it to detect planets by understanding the way they move around those stars. In more detail, the topics we covered through this lecture include the law of universal gravitation and how we can combine that with the knowledge we learned about circular motion earlier in the course to understand how objects move in their orbit in order to work out, for example, the orbital period of a geostationary satellite. We learned about how stars are born, and included in that we had a discussion of the gas laws that you learned earlier on in this course, including pressure, volume and temperature and how these relate to one another. We then moved on to talk about the power source of stars, bringing back the things you learned in topic 11 about nuclear fusion and extending those ideas a little so that you could understand the proton-proton chain by which the sun burns hydrogen to form helium, giving off lots of radiation. We then spoke about the colours of stars and how understanding what we call black body radiation allows us to take the colour of a star and work out from that the temperature of the surface of the star. We then moved on beyond just looking at the colour of a star to look at the spectra of stars, and this refreshed our memories about absorption and emission of light by gases and we introduced the concept of absorption spectra, which we can use to determine what a star's made from. We can determine the species that are in the atmospheres of that star, of a given star. Finally, we went one step further and used that absorption spectrum, coupled with the Doppler effect, which you learned about in topic 7, to find out how we detect planets and other unseen companions to distant stars by looking at how the light from those stars is redshifted and blue shifted as the star wobbles back and forth around the centre of mass between the planet and the star. In the activity for this topic, you'll learn one other thing about astronomy that's very, very important. You'll learn about how your eye adapts to darkness. You'll also learn how light pollution spoils our view of the night sky. One important thing to bear in mind when you go out to complete the activity for this topic, and also if you're ever going out to just look and wonder at the beauty of the night sky, is that it takes a long time for your eye to adapt to the darkness that you're experiencing when you're stood out on a moonless night, particularly when you're away from streetlights. In fact, if you go out on a very dark night, it can take 15 or 20 minutes before your eye's even vaguely close to being fully dark adapted, before you can see the faintest stars you can see. And the process really actually takes of order 1 hour before you're fully adapted to the darkness. If somebody shines a light, turns on a white light torch for example, that resets the clock and you have to start that adaptation process again. So if you go to observe the night sky with your friends, if you go down to the beach, if you go to the middle of Australia somewhere to a properly dark site, make sure your torches are off, you don't turn your phone on to look at your email because then you reset your clock. One way to get around that is to use a red light torch. The part of your eye that is sensitive to very faint light is not sensitive to red light at all. And so if you use a torch that only gives off red light, or you have a red filter on the front of your torch, that won't damage your dark adaptation. You'll also see how light pollution spoils our view of the night sky. So the street lights and the security lights and car headlights all, for some reason, are poorly designed, and some fraction of the light they emit goes off into the night sky. You'll have seen this when you've seen poorly designed security lights on the side of buildings that are shining up and illuminating tree branches above them. I always wonder whether people who have security lights like that are particularly terrified about burglars coming in by helicopter, because that's the only kind of burglar that you detect with a street light that shines upwards. Nevertheless, roughly 30% of all the energy we put into lighting our cities is wasted shining up into the night sky, and some fraction of that is scattered back down towards us, producing an orangey, horrible glow that obscures the fainter stars and makes it much harder to see the night sky. And you'll see that to some extent during the activity for this topic. What you also might learn, if the weather in Sydney is particularly bad that week, is how clouds interfere with our astronomical research. I will apologise in advance if bad weather means that you don't get to do the topic, but I really hope it won't. But clouds are the bane of our existence as astronomers, which is part of the reason that telescopes like the Hubble Space Telescope are launched to space. Part of that is simply to get away from the pain in the backside that clouds and the atmosphere produce. The Anglo-Australian telescope up at Siding Spring Observatory that we use to search for planets is clouded out on approximately 1/3 of the nights of the year. So if we are successful in getting 10 nights of observing time, it's likely that the sky will only be clear enough to observe on 6 or 7 of those nights. So putting telescopes into space is hugely helpful and beneficial to us as astronomers. Anyway, thank you for your attention and good luck with the rest of the course.
Special thanks to Sebastian Frick for filming and editing this video.